All right, how we doing, everyone? Doing good? Okay, so today we're gonna make it to really quick. We're gonna go over the final exam reviews. So what I was just saying, if you keep all your homeworks, all your computer assignments, all the written homework assignments, the exams, and all the little quizzes that I've always given you, and honestly, you'll be fine. Done? All right, easy. But for today, I will be using the following material. Let's grab this puppy. Actually, nah, Chrome. And let's pull this puppy out. EE360, and we'll just walk through it. And here's today's lecture. And let's just go over it. Well, actually, let me just go over what I can remember. So remember from chapter 1. Chapter 1. Does anyone remember what chapter 1 was? Remember that? Alright, so you already know what's the first word, right? Oh yeah. Just kidding, no. I don't even know. But do you know what a function is? It's a rule that basically takes some elements from set x to another element of, let's just call it f of x or y or something like that. It takes elements from a set x, so elements, to unique elements. Remember that stuff? First definition, okay? And then same thing with, if we go to chapter 2, there's transformations, okay? So, easy one. And then there's other things we talked about in signals and systems. So one of the other things that he was talking about, I thought Stevie was talking about, was what is, should we go backwards or forwards? Let's go forwards. What's an energy signal? Where it's power and neither. How do you spell neither? Is that it? How you spell it? Neither energy. Okay, remember that? So, and he commented to me this, and he was like, David, apparently everyone was just drawing pictures of what an energy signal is, and they don't know what an energy signal was. They just knew what it looked, but they didn't know how to explain it. So, let me see if we can derive the mathematical equation for that one. I don't remember it, but we'll try to figure it out. We're going to do analogs. So if I were to draw the following, let's do the following signal. Yeah, there we go. You like that signal? Pretty fun? Oh, T. Okay? X of T. All right, we're about to derive this equation. So I know this is an energy signal. You probably don't. But what we're going to do is we're going to go, so the energy of x is equal to, what I'm going to do is we're going to add every point, x of t, and what do we do? I'm trying to remember. At every point, and do we do an absolute value? I'm trying to remember it. Oh gosh, it's not coming to my head. dt. At every point, I know it's going to have an infinite, it's going to have this. It's going to have an integral. You're going to have to add every point. And if this is finite, then it's energy. Okay? So I think this is the bare minimum from what I remember. This is energy. It says finite. Finite pulse. Okay? So if you have a finite pulse, it's just a blip in time. It definitely don't have power, but it's got a lot of energy in it. See? Just add all those points. So I don't remember the full definition, but that's like, I guess, how I would get it. Okay, so. There we go. That's all I was missing. Because okay, the reason why there's a squared was because what happens if he gives you the following signal? This. All right, and if you add every of these points, okay, if you add this to this, what are you going to get? 0. Okay, and obviously there's energy there, so that means you got to take the absolute value of of this entire thing so that you get energy. Okay? So, okay. And then that's the reason why we have the squared term. Just to keep everything positive. Okay? And the squared also helps with mean squared. Actually, no. I'll show you this. So this is energy. So now what about power? So if I give you the following signal and it just does this. Let's draw this. Oh, you like that? And it just does this forever. It just zigzags like that. All right. It's from to infinity time, and from t is equal to minus infinity. Okay, remember that stuff? So if you have this signal that's just periodically moving, okay? So what I'm going to try and say is, okay, how do I want to explain this? If we want to add all these points, right? P of x, we're going to have the same format from infinity to infinity, t, remember that? We're going to have the same format, right? We're going to add every point, right? But if we add all these points, right? Absolute squared, okay? This is going to go into infinity, which is bad. So what's another infinity we can like divide out so that the infinities cancel each other out? Time. So the entire time. So as the integral gets bigger, as this t goes to infinity, then this also gets bigger too. And I think, is this t tucked in? Whatever. This t is basically the entire length of the signal. So that if this is infinite and this is infinite, the two infinities kind of divide out to give you a constant power. But if you try to get this signal, this pulse right here, it's going to go to 0. So that means the rule is, let's see, if you try, there's no power here. Okay, if the power is 0, that means there's energy. And if the, if the power is infinite, no. Okay, the rule is, I only remember this one. If you're getting 0 power, you're guaranteed to get some energy. That's unless the energy is 0 or something like that. Yeah, you can figure that out. But is that making a little sense? Actually, the limit as t goes to infinity, or to infinity, t goes to infinity, something like that. Is that clear? All right, I'm just pulling this all from like the top of my head. But that's energy and that's power, okay? You can do the integrals, practice those. But what about neither? And don't draw the pictures. You gotta explain this. So what happens if we get a signal that does this? It just blows up, right? It's going to, okay, it's blowing up. So one thing I'm gonna ask, let's think practically. What system actually can do this? It just goes to infinity and minus infinity. It doesn't exist. So that means it's neither energy nor power because it doesn't exist. It's neither an energy or power signal because it doesn't exist. Let me just draw a box this way. Okay, here's T. So if you try to, let's call this one, I don't know, what letter should I choose? L? L of t, okay? And if you try to punch in this L of t into there and into there, you notice that this goes to infinity, but this is actually a bigger infinity if you think about it. And this smaller infinity is not going to catch up with this huge infinity, so it's just going to blow up. Infinite power, which means it's bad. It doesn't exist. Same thing with infinite energy. Doesn't exist. It's neither energy or power. It's not bounded input, bounded output, or this is neither. So don't worry. So that's conceptually, you can do the math if he throws in, suppose I give you a signal x of t is equal to alpha of, no. He's going to give you a constant alpha and then e to the capital A, and should I do this? Alpha t j, no. Should I do that? Oh, no. There's got to be an imaginary signal and there's got to be a constant. Actually, no, this is actually driving my OCPD going crazy. X of t is equal to a e to the, we need a damping factor, a of t, e to the j b of t. There we go. So you have a damping factor and then you have this oscillation. So if he's gonna ask you, all right, make this a power signal, make this a power signal, an energy signal, and neither, you know how to do that, right? If you want a power signal, here you go. You have this nice sawtooth wave, it's periodic, there you go, power. Which is a mean squared or root mean squared. Square root it to get voltage or RMS voltage if you want. Here's energy, okay? And here's neither. You know what to do, right? He might throw that question on you. The basics of signals. Any questions on that? Nope. All right, next page. So now let's dive into the next chapter. Hopefully we can finish and we'll hopefully finish chapter 2, systems. Okay, so what you all remember? Remember? So, oh yeah, there's all those properties. So like linearity, and then there's what other properties? The scaling, and what else was there? There's, I think, you know, all those etc. I'm just gonna do this, etc. Okay, remember that stuff? So that's everything we're gonna cover. Okay, everything we're gonna do from there. What else? There's also block diagrams. Okay, there's the DF1. Remember that one? This one's a simple one. Feed forward, feed back. Okay, remember that? It's just the direct one. We have all these zeros that are in the front. We all know what zeros are right now. And then we have all these poles in the back. Okay. So then what happens if he makes you draw a direct form 2, DF2? You know how to draw that, right? Feed back, feed forward. Remember that? But then there's the special trick where everything in the middle this one has less components. Okay, so if he asks you to draw this, everyone's gonna get 100 on it, right? Sweet. And then the last one is the TDF2. Remember that? So we want the benefits of a direct form 1, but we also want to save some money too. So we're gonna have this weird feed forward path and feed back path. And then we also like save components. Okay, remember that? And then also from this we also did difference equations, diff EQs. So remember all those for loops and stuff? You can all implement for loops, right? If he asks you, all right, implement this in code, it's gonna be easy, right? Yeah, it should be easy. And then there's the state space equations. Everyone's gonna remember that? There's 2 of them. There's analog, and then there's digital. Digital. Okay, remember that? Where this one, everything's gonna have, okay, if I were to do this, how do I wanna do this? Where the next state for the analog is actually gonna be your differentials. Remember that? Q of t. And then this one, the next state for the digital is just going to be Q of n plus 1. If Dr. Stuber asks you to find the derivative of Q of t or the next state of Q, is everyone going to do that? Easy? That's it. These are the 2 big things that we talked about. And how do you get these? You get these from either this, or actually not that one, or this. So if he asks you for direct form 2 block diagram or the transposed version, and he asks you for state space equations, can you do them for both analog and digital? Easy, eh? All right, page 3. All right, page 4. What was the next thing we talked about? All right. Remember what we did for convolution? What was the bare definition? Let's put in analog or digital? Analog. Remember that? What's the governing equation for that? We're gonna do the entire signal. Let's call it tau to infinity, right? Let's shift. Let's change. Let's keep x of t constant, x of tau constant, okay? And then let's shift h, t minus t dt. Remember that? And you know what this means, right? Do you understand what this means? Practically. Yes or no? No, practically. This stays still, or this is constant, or stays still. Okay? And then this one is shifted. So if you were to draw this, let's say it's like some pulse x of t, something like that. This stays constant. You don't move it. Yeah, you don't move it. It just stays there. It just doesn't do anything. The thing that does move is h of t. Let's just call it h of t. Let's say h of t was this. H of t. Okay? So that means what's h of tau, or this thingy? It's going to be h of minus tau. And then this is the thing that sweeps. Okay? Where actually, let's call this sweep t. Where if t goes this way, then this thing just moves with time, okay? Does that make sense? Okay. Someone's probably not getting what I'm saying. Let's talk about the digital case. Actually, should I finish this one? You want to see the other one? Actually, nah, I'm not going to show you that one. I don't have time. We're going to try and rush this one. Y of n is equal to h of, what do you call it? N convolved with x of n. Okay? I'm going to do the digital case now. Right? This is analog. And this is digital. Okay? What's the rule for this one? Summation. Let's use k minus infinity. K is equal to positive infinity. And let's keep h constant. Okay? That's going to stay put. It's going to stay frozen. And then we're going to shift x. Okay? And you know what this means, right? Remember that cool trick? Look in one of my previous notes where let's say h is this. 1, 2. Where this is h of k, right? It just stuck there. Okay? And then if x of k was this, or let's say x of n is this, right? So if you wanted to solve for some y of n, remember that cool trick I did? It was like, here's h of 0, h of 0, and then this was x of 0 plus h of 1 plus h of 1, and then this was x of minus 1, and then this one here is x of 1, x of 0. Remember that cool stuff I showed everyone? Y of 0, y of 1. Remember that cool trick? Where this one, okay, how do I explain this? This here is constant. Okay, this is constant. We're using h of k, okay? Here's h of k, it's constant. Right? Right? It just stays there, okay? This is h of k, h of k. Right? The thing that's shifting is this. This is shifting. Okay? So that means when we're shifting, this is like the mathematical way. Okay, where this is actually okay. This is going forward, right? H of k is going forward, right? So we're going like this, forward like that, right? But if we were trying to do this shift and like flip, shift and flip, this right here is traveling backwards like that, right? And how do I know that this is 0 and this is 1? Look at this. See? Cool, right? Everyone's gonna do that on the exam if he gives you a digital convolution, eh? He's gonna ask you this. All right, convolve these two signals. Actually, that actually might be a good question he might ask. This is page 4. Should I get to the meat problems? Okay, I'll get to the meat problems. So what I was meaning by that was, okay, we just took an exam 6, right? So let's say it gives you x of n is equal to, I don't know, alpha of n, u of n, and h of n was equal to beta of n, u of n, something like that. I'm just going to give some random signals. And he says, problem 1, solve using convolution. Okay, easy, right? Do not, and he's going to say, do not use ZT. All right? Simple? Huh?
Or ST, right?
ST?
Low cost?
No. It's digital.
Oh.
That scares me, man. You're scaring me.
Oh, not bad.
You're scaring me.
I was thinking X of T or no, not bad. Ignore me.
Okay, and then problem 2. Do it again. With ZT. Easy? And then he's gonna say, he's probably gonna do this. Compare. And then this is where you start choking because you're like, oh gosh, the same problem's on there 3 times. I don't know why. And then, oh, you want something even crazy? This can be found. This looks like an impulse. Looks like impulse. Because look, we have a residue and a pole. We have a res, and we have a pole. Or well, let's put some constant. Res, and this is a pole. Okay, right? Remember that stuff? So what happens if he gives you a difference equation like I don't know, a y of n minus 0 y of n n minus 1 is equal to x of n. Do you know how to find the impulse? Can you find that? All right. So then he's gonna make you solve this. This is probably problem 3. Fine. Or actually not problem 3. This might be problem 0. 0. Find h of n. Okay? And then he's probably gonna make you do this where x of n is equal to h of n. And now start using the convolution. Is that crazy? You never know. I don't know. He might do that for you. I'm just saying what I think he might do. All right. What was the other thing we talked about in convolution? And you probably saw that h of n, right? Pretty scary, right? How do we find it? Remember that? Find it by doing these. Find your feed forwards and feed backs. And from the theory, if you had something like this, y of n is equal to, actually, no, I actually want to do this. Y of n minus y of n minus 1, right? What does that look like? This is just the feedback path. This right here is the feedback, where c of n, this is c of n. Actually, how do I explain this? Okay. How do you find h of n? The impulse response. How do we find the impulse response? Kick. Kick. Okay. How do we kick the box? The delta function, right? So how do you build these feed forwards? You don't know? Come on, man. Just you gotta look at your inputs. Plus x of n minus 1, okay? Simple stuff, right? This might be a delay. B0, B1. Looks simple, right? What happens when we put a delta function in there? What do we get out? Remember that stuff? Easy? I hope it is. So this is how you would find your h of zeros. And that's the easy one. Okay? This feed forward right here is h of zeros. Remember that? Now how do you find h poles? You kick this box too. So you build this part. Here's this part. It's just built. Do I want to build this? Yeah, let's build it. It's going to have a minus. How do we do a minus? It's going to see a minus. 1 plus. And this is going to be a minus. Okay, there we go. Build. Feedback system. Okay, remember that? So AKA, this is just the aux equations. And then solve for the auxiliary equations as normal. You know how to do that? Easy? And then we guess the general equation, y of feedback or something like that, n is equal to c, this is digital, lambda, hold up, lambda to the n u of n. Remember that? C1, lambda 1. Where if we kick this box right here, right? What's the initial condition that you got to memorize? That's what we kicked. We kicked the box at that time. Remember that? Easy, right? And then from that you can solve for h of poles. Okay, easy, right? This is a lot of material, right? And now let's go over to find our little thingy. So once you build h of z, right? And now you have h of p, right? Find the total response, or not total response, the impulse response of this system. How do you do that? What's the impulse response of the system? How do you find the impulse response? Your input is an impulse. So now what do? Come on, it's chapter 3. Convolution. C of n. What's C of n equal to? What's that equal to? Done. Now what's y of n equal to? Done. And you know what we just did? It's a ZSR. You gotta remember that on the exam? ZSRs are just basically impulse responses. You're just kicking boxes, finding the feed forward paths, finding the response of the feedbacks, and then finding a total impulse response. Impulse response. And now you're probably saying, but David, you just said the word total response, right? Okay, how do you get that total response? So suppose he gives you this. What does that mean? What are we doing here? Zero input response. Okay? We ground the input. What's that mean? That means we have no feedback. Actually, okay, because someone's probably going crazy. What's C of n equal to? Easy? Come on, guys. You guys feeling alive? Oh, we're in pain. So that means what does that your circuit actually look like? Or not that. You know why I didn't do that? Because this is also grounded. You know what's going on in here? You have memory. And you know what happens when you have memory? This is Dr. Steerberg's. Steerberg's values. Okay? So that means you're going to get the same poles. Y of n minus y of n minus 1 is equal to... Come on, guys. 0. Okay? So that means what do? This looks like an ox equation. Or minus 1. Come on. Right? Easy. But then this time, when you're trying to solve for y, z, I, r, C1 of lambda 1 to the n u of n, where he gives you a condition. Where this could be y, z, I, r of 0 is equal to, I don't know, k. Something like that. Easy, right? And then total response is just y, what do you call it? YZSR plus YZIR. Okay? 40 points. Just kidding, I don't even know. This right here is YZSR. This is YZIR. Solve for ZIR first, then ZSR. ZSR is pain. Pain. And easy. Easy. Okay? Good? Man, class, you okay? We're all shaking? Oh. 7. Alright, hopefully we gotta finish this really soon. So then, do I want to brush up on this? I don't know, man. State space equations. Remember that stuff? There's 3 variants. You got the, what do you call it? R4. Do I want to do this? You got the analog case, which basically you're going to have to do either all those weird Q of T's. Remember that? Or you have to do this. Q of S or something like that. Was that the other one? Yeah, this. Q of S. Okay? So remember, this was equal to some crazy matrix. So we had like those like, it was like A, Q of T plus B, X of T or something like that. Remember that? But for this one, well, how do I remember this? State space equations. You're going to get these equations, or Q of S, S, something like that. If we go into the Laplace transform, remember that? We're going to get this S that comes up, okay? He's probably going to ask you to do the same thing again, y of S. Solve for y of S, solve for the state space equations. or solve for like the impulse response. Okay, that's the analog case. And then digital, you're gonna have the same thing, q of n plus 1, but then this is gonna go to z q of z. Okay, where then you have to do the same thing again, y of z, and then solve for that weird equation. I think it was like I actually don't remember. Come on, do I remember? Z I something? I actually zi minus a minus 1 b.
Oh, there's a C in front of the inverse.
Yeah, c b plus dx of z. Remember that? That's what's going to be on the exam too. So either this is probably like problem 1 or problem 6 or something like that, and this is problem 7. Okay, do it without going into Laplace or z, and then do it again, but with z or Laplace. So I honestly don't know what he's going to throw at you, but it's going to be one of those. Oh yeah, there's another thing I got to talk about before I move on. 9.
Steady state.
Huh? Steady state? Okay, steady state. And I have a great equation for you. He's going to give you this equation, I know. Okay? All right, solve for the impulse response. Or not really, just solve for the transfer function of this. You know how to do this? Okay. Does that make it easier? V out of S. I'll search you out.
Where you give the dy of t over t plus 1 rc with y of t equals 1 over rc x of t.
Actually, wait, what? Okay. 1 SC. Okay, where we're going to have 1 divided by SC. R plus 1 over SC. Okay? And then it becomes 1 plus SRC. Done. Okay? Easy? And now, how do you find the magnitude of this? V out of S. Okay? Or actually, how do I want to do this? Let me show you what I'm trying to do. It's also going to equal 1 plus j omega. Do I want to show you that? 2 pi f of s. Because, well, s needs to equal j omega. So j omega rc, okay? Remember that? Of 1 plus omega rc squared. Okay? Easy? That's the magnitude response. Okay, so what I'm going to try and show you is what happens if he gives you Vn of t is equal to, I don't know, sine omega t, omega naught t. Okay, what's V out? You're going to realize that this is an eigenfunction. Or eigenfunction. Because we have an omega here. This actually can be derived into, I think what I was trying to say was, this is a pole. It's going to be, well, hold on. This is a pole. The pole is at e to the, e to the minus t over RC u of t. There you go. See that? This is an function. So what was I going to try and say? That's an RC. Yeah, this is definitely an RC. I was trying to say something. Where if you look at this frequency, right? And if you wanted to find the output using the actual transfer function, what he's telling you, you have to do this. S is equal to omega naught. And then V in of t. And then I think you gotta multiply it by e to the j h, or the angle of h of s is equal to omega naught. Easy? So what I'm trying to say is V out is gonna have a change in magnitude and a change in phase. Okay? So that's what he means by this steady state. So he's going to give you an eigenfunction like sine, something periodic. It's going to be real. Definitely going to be real. So if it's like 1K. Okay, let's punch in numbers. 1K. What's the output? What's the output frequency? It's going to be 1K. Okay? So that means, what does this have to be? 1K. That means punch in 1K. Okay? And then you already know how to get the angle, right? Angle of H is equal to, hold up, minus, hold up, it's going to be minus tan minus 1 of omega RC. Okay? And then just punch in this 1 in there. You have a change in magnitude, change in phase. That's what he means by steady state. And then there's an equivalent thing that you can do with Z transforms. Also equivalent in ZT. So that's what he means. Okay, so I think he's probably gonna throw this, or he's gonna throw you a digital version of this. And it's I remember reading it in his book, so that's the only tips I can actually give you. So rip. I'm sorry about that. What was the other thing we covered? Well, if you wanted to, I can cover this again. It's a Laplace transform. Was it chapter 4 or something like that? I think it was chapter 5. Remember all that stuff? L of x of t is equal to x of s, which is equal to, we're going to go analyze the entire thing for time, of x of t e to the minus st dt. Okay? Everyone can do that, right? Everyone's going to remember the following properties. The unilateral LT, remember that? So you can do your ICs. Okay, so if he gives you like a predefined function or predefined number like y of t is equal to 0 minus is equal to, I don't know, k or something like that, you can do that. Remember where you have y of d, okay, like y of t dy dt is going to turn into s of y of s minus y of 0 minus. Remember that? That's what we're going to do. But I don't know what other properties there are too, but that's the big cheese of the class. Easy? And he could throw, well, obviously remember what's the unit step? 1 over s. What's a ramp? It's basically, how do I want to show you this? It's 1 over s squared or something like that. I was trying to say, if you look at what I was trying to hint to you was, if you have x, if you have a pole here, if you have a pole in the middle of the Laplace transform, what's the residue of this? Well, let's call it 1 or something like that, right? Well, what's the pole? This. So that means if we transform this back into the time domain, you're gonna get e to the 0t u of t. What's e to the 0 u to t? U of t. Easy, right? But what happens when you have two poles? Or two poles at 0? So that means you're gonna get the following: 1 over s times 1 over s. That means you have to do your like partial fraction expansion. I think a s plus b s squared or something like that. You have repeated roots. But this will eventually get you this or something like that. And then this will give you the ramp function, which is equal to the convolution. How do you generate it? It was like, oh, t squared or something like that. That's all I remember. T squared u of t. Or is it 1/2? I don't remember. But you know what I mean, right? Simple stuff like that, right? You can analyze poles. PZ maps. You can understand those, right? Residues. Poles. And you can get the following: res e to the pole. Okay? Oh, don't forget the unity. Don't forget. Don't forget. Okay? Easy? And then the final thing we covered, and I gotta wrap this up because it's getting way too late. Z transforms, which I don't know what chapter that was. And it's basically the same thing, where x of z is equal to, what was it? We're analyzing the entire signal of x of n, and then we multiply it with z to the n? Or was it z to the minus n? Okay.
Well,
Minus n? I don't remember. You guys should remember. This is your guys' exam. We just took an exam, exam 6.
That's why I feel like
I think it was just an analog is negative ST, but this was just
It is n.
Positive n?
Yeah.
Easy, right? We can find all those poles, right? And we can do the same thing. Unilateral zt, right? Where it's basically, z to the n minus 1 can transform into x, z to the minus 1 of x of z plus, don't forget this, x of 0. Oh, no. Minus 1. Remember that? Easy, right? And then, what else was that? And then everyone can basically understand this, right? If I were to draw a unit circle, and this, we gotta end this soon. I wanna go home. If I were to draw a pole here, is it stable? How do you make it? Is it stable or unstable? Huh?
if it's left-sided,
And it's
it's unstable.
that should be.
Is it stable or unstable? Come on, trivial. I'm scared, guys. I'm really scared. Stable. What happens if I have a pole right here? Unstable. If I were to go right-sided or right-sided, okay? But how do you make this? How do you make this stable? Or not? Or how do you see? Blue. How do I make this stable? If I wanted to, you would have to go left-sided. Okay, but it would be non-causal. Making sense? And honestly, that's it. Honestly, this is an entire class. If you can go over all this stuff, Laplace, C, this is the only thing I would probably highly recommend everyone reviewing. Steady state for both the Laplace transform and the Z transform. It's the Bode plots. You know what I'm talking about? Okay, let's talk about Dr. Baker's stuff. Remember all those Bode plots? Okay, steady state. State 2. Bode plots. Okay, where you had some, literally the transfer function. Look at your transfer function, h of f, which is equal to 1 plus jf over f3 dB, okay, where you had the following. Let's make this 0 dB. Okay, remember that stuff? And then you would look at the frequency, and then this right here is f3 dB, and you would just calculate your output based on this, right? And if I were to do a phase response, right, this looks like an RC circuit. Okay, what's the phase response? I'll give you a hint. Okay, actually, do I want to do this? Okay, what's 1 decade up there, 1 decade up there? F3 dB divided by 10. 10 times F3 dB. You guys are killing me. Okay. And what's the phase response right here? What's the degrees that we have? 0. And then what happens when we start pumping up in frequency? It's 90. Yes, 90, because this right here is minus 45. Easy? 220. So that's the only thing I can recommend. And else, this exam is going to probably be 8 questions long. It's going to have definitions. Well, not the definitions. Solve for energy, solve for power. Do you know what if it's not neither? Can you do difference equations? Can you do ZIRs, ZSRs? Can you kick your boxes? Can you find the pole response or something like that? The response of a feedback circuit? That's all convolution. And then when we jump into the Laplace transform, can you do all those residues? Can you find the poles? Can you do state space equations for both convolution and Laplace? And then there's Z transforms, digital, where you do the same thing. Find the state space equations, block diagrams, and residues, poles, unilaterals. And that's it. That's the entire course. Man, we fit a lot. Any other questions? Oh, go home. All right, this is the last lecture of the entire semester. Thank you all for coming. And we will all see you guys Monday.